But what's important is there's no calculator for this question. On the open-ended, you're going to get 3 with calculators and I think 3 without calculators. Most of the stuff with calculators that'll be questions that we'll encounter later in the course. Usually this first unit stuff on limits, this is typically going to be non-calculator stuff. Okay, so let's look at this guy. The question says, this is also going to be true for just about all these. Unless otherwise specified, the domain of the function is assumed to be the set of all real numbers. Well, they're giving us the domains of this piecewise function. They give us the piecewise function, and then for part A, they're asking, it says, let f be the function defined above, where k is constant. For what value of k, if any, is f continuous at x equals -2? Justify your answer. Okay, so take a second and just think about how you're going to say this in a way. And it's not about just getting the right answer. It's that justify your answer is important, right? You need to include the relevant information. When you look at the way that these open-ended questions are graded, there's literally there's some boxes. There's a scoring guide that the people are gonna go through, and they're gonna look for specific things. So try to think about the specific boxes that you probably think you're gonna need to check for this. Just take a second, talk it over. So here's the k, right? If we want to choose that value of k, how does that come into play here? What's significant about k if the function is constant? There's the value of k that we have to set. What has to be true about k? Okay. So -2 is going to be that's the boundary where k comes into play. But it's not. Now choose your wording carefully. How are we going to show this? If it's going to be continuous, what are the criteria for continuity? For a function to be continuous at a point, what has to be true? Say it again. The limit has to exist. Say it again. Now, I'm gonna put a page in here. Let's just kind of review this topic really briefly. Let's write down the criteria. So if a function is going to be continuous at x equals k, what would have to be, or x equals a, what would have to be true? Well, Amber already said the limit of the function as x approaches a exists. What else? Say it again. Okay, good. So the function has to exist. Meaning the function is defined at that point. And what's the big thing here? In order for I think you were getting at this, Madeline. So the function has to exist. The ants approaching from opposite directions have to anticipate stepping on the same point. The function has to exist. And what about the relationship between these two things? They have to be equal. Good. So the third criterion is that those two things are equal, right? Okay, so that's how we want to address this problem then. We want to just show that for the limit to exist, now this is a piecewise function, so how are we going to show that the limit exists? Or how are we going to set the value of k so the limit exists? Right, this is the part that we're focusing on up here, isn't it? Set what equal to each other? By the two functions, you mean like this and this? Okay, but they have to be limits, right? With the way we have to do this, and that's one of the things they're going to look for here when they're grading this, I'm sure, if we look at the criteria. for part A. At most 2 out of 3 points if mathematical notation for limits is missing or incorrect. So you're already limited if you don't, no pun intended, if you don't, if you're not including limits in your description, right? So if you want to get all 3 points, these are the 3 boxes that they identify that you need to have, and they make sense. You have to have the limit from the left, the limit from the right. We have to show that those, in order to make those equal, we're going to set a value of k. And then we have to also show that after we've calculated what k needs to be for the limit, we just need to also include that the value of the function is equal to the value of the limit there, right? The bottom piece of these two, this piece right here, is including -2. That's going to be easy to do because when we take the limit of this piece here, the x cubed plus 2 piece, the limit, that's a function that we're going to be able to evaluate the limit directly with, right? So the value of the function is going to be what the limit anticipates. In other words, the ant is going to step where he anticipates stepping when he approaches from the right. Okay, everybody get that? So we just want to include that one little other piece there to get all 3 points, though, that, we're meeting all the criteria for continuity. So here's the solution then, and this makes sense, right? You get this is, but you have to show this notation. The limit of f of x as x approaches -2 from the left. If we're approaching from the left, that's going to be that top piece, isn't it? Right? So as x approaches -2 from the left, we're just going to evaluate this thing directly. We're going to plug in -2 for all the x's. And what we're left with then, all the x's disappear, and we're left with some expression involving k's, right? Bottom just gives us 7. Top ends up giving us 2 minus 2k. So there's the limit as we approach -2 from the left. As we approach -2 from the right, that puts us on this piece right here, right, where x is defined as being greater than or equal to -2. And so if we evaluate that, we just get -6 if we plug -2 and then evaluate, okay? So then I would add something else here then. So weren't we finding k? Isn't that the whole point of this thing? Okay, so they didn't actually do that, did they, in their solution, did they? Oh, there it is down there. Okay, yeah. Okay, and we also want to say this. See, this is the other point I'm making. The f of -2 is -6. These two would be the same, wouldn't they? But you have to include that piece. If you don't include that piece, you're not guaranteeing continuity, right? The function has to exist there too. And then the math part of this is just we're setting those two equal to each other, right? This is the limit from the left, that's the limit from the right. Set them equal to each other and solve for k, and that's it. Make sense? Okay, but you got to include all those pieces. So what about part B? What type of discontinuity does f have at 0? Give a reason for your answer. Okay, so what about, here, let me cover this stuff up at the bottom. Okay, so how are we going to approach this one at 0? Say it again. Is this, are you supposed to be scoring? Yeah, does it ask you to do that? Yeah, I would definitely. That's what I was hoping you guys were able to do, is just score your own based on because then it forces you to look in at all that's so you can do that, right? Has anybody been doing that? It won't? Oh yeah, that's okay. That's it. Yeah, right. You have to click on. So when you're scoring your responses on these, there's some boxes. It'll show you the number of available points. Like it'd be if it was a 2-pointer, it'd be 0, 1, 2. Just click on the highest one, and see which of those. See if you hit all those points. Okay, does that make sense? And then if you click on one, it'll say you have to get like one of these boxes instead of both of them. No, I think I'd rather you guys just score it. Just based, then it forces you to really look at the criteria. Okay, so what about this one then? How are we going to know what type of discontinuity it has? There's a break in the function here at 0. So what do we got to do? Like if it were a non-removable continuity, like if it were a break in the function, how would we know? Right? The limits would just be different from the left and the right, wouldn't they? So we want to take limits from the left and limits from the right and see what happens. And then we know the actual value of the function there. So either that point is going to align with, with if it's a hole, either that's going to fill in the hole or it's not. Probably not, because it says it's got a discontinuity. So this is a 2-pointer. Here's what you're evaluated on. The 2 points they're looking for are taking the limit from the left and the limit from the right and the correct answer. Okay, that's it. So if we do this, the limit from the left, we're going to be taking from the left, we're looking at that piece of the function. If we evaluate that directly, we get 2. The limit from the right, we're taking the limit of the piece that has the exponential part. If we evaluate that, we get 2 also. Any questions about how they get those answers? We're good with that? Everybody? Everybody good? Okay, so then we see that the limit from the left and the limit from the right agree. So that means that the two-sided limit exists, right? This is important. The limit of f of x as x approaches 0 is 2 because the two one-sided limits agree, but the value of the function is 0. So therefore, it's a removable discontinuity. It's just 1 point that's been shifted off the function, okay? And you want to make sure you include the words removable discontinuity. Okay, questions on that? Okay, next one. Find all horizontal asymptotes of the graph. Okay, so when we're doing horizontal asymptotes, those are always what kind of limits? Infinity or negative infinity, right? Okay, so if we want to find, here we're going to have to take the limit of this function as x approaches positive infinity. We're going to be in the purple piece, right? As x approaches negative infinity, we're going to be in the orange piece because it's a piecewise function. So then all we would do on this one is just take those limits, right? So how is this one scored here? Yeah, they just want that, and there's 2 points, and they want both of those limits, right? They want to see the limit as you approach infinity, limit as you approach negative infinity. So the purple piece is right here as we approach. Did I get that backwards? I got it backwards, didn't I? Yeah. That's supposed to be, that's negative infinity, and that's infinity. So if we take the limit of the purple piece then, as x is approaching negative infinity, well, look, we got a rational function here. How do we deal with the infinite limits of rational functions? This is really simple stuff, right? You don't have to, see, I'm surprised. I don't think you have to do all this stuff. I don't think you need that step right there. I think you can just jump right to the limit. I really don't think you have to show all that, because we know that we have a rule here. If we're taking a limit of rational functions, if the degree of the top polynomial is equal to the degree of the bottom polynomial, the limit's equal to the ratio of the leading coefficients, right? That's what I would say. I wouldn't bother with all this stuff. I would jump from here right down to there. And the reason is because what I just said, just write that out literally. The limit as x approaches negative infinity of a rational function where the top and bottom have the same degree polynomials is the ratio of the leading coefficients, right? That's it, okay? That's a lot of writing to do. I mean, we went through those steps last year at one point, but you don't really have to do them. The other thing you could do is you could say the limit of this function is equal to the limit of x squared over 3x squared because it's going to be the leading terms are going to be the dominant terms. And then algebraically, that just becomes 1/3. Okay. Whoops. Okay. Questions on that? But I would avoid having to show all that math, unnecessary. Okay, so then what about the limit of the orange part as we approach positive infinity? As we approach positive infinity, this is going to become, we're going to end up getting, see, this is the approach they took in this one, right? We know that the dominant terms are going to be the e to the x terms. The 2 is going to be background noise, right? E to the x is going to explode as x approaches infinity. So the limit of this ratio just becomes the limit of the ratio of the dominant terms. And algebraically, that just becomes -2 because the e to the x is canceled. Everybody see that? Okay. This is the important step. Be honest. Everybody get that step? How we're able to say that? Give me 1 to 5 on that step. Okay. Okay. Again, justification. That goes away because these terms are going to explode and that one doesn't. Okay? All right. Next question. So this guy. This is a, what is this here? There's the function. So this is revenue. The total accumulated revenue a company has received up to time t is modeled by this piecewise function, where R is measured in millions of dollars and t is the time in years since 1980. Okay, so first thing is find the limit of R of t as t approaches infinity, and then explain the meaning of that limit in the context of the problem. So which piece, top or bottom, are we going to be evaluating with the limit? Bottom. As t approaches infinity, we're in the bottom piece. Look, it's another one of those horizontal, those are easy, right? Horizontal asymptotes. We have rational function. Top and bottom polynomials have the same degree. So we look at the ratio of the leading coefficients and we just get 100. Okay, so we want to be able to take the limit. And look, see here they didn't go through all that mumbo jumbo, right? Here they just showed, that's how I would have done the last one too. We just get 100. And then of course, what's that mean? As time approaches infinity, then the revenue is just approaching some, it's approaching some value above which it'll never go. As the time increases, the total accumulated revenue of the company approaches 100 million. That's all you got to say. Okay. Give me 1 to 5 on that. How we doing? Good. Okay. Part B. Is the revenue function continuous at 20? Well, this is just another limit question, isn't it? Right. We're going to take a limit from the left, a limit from the right, and the value of the function is determined by the bottom piece. Right. So we would just show, we got to show both of those one-sided limits and then justify the answer. Okay. Continuous at 20. So limit from the left would be the top piece. Limit from the right would be the bottom piece. So the limit from the left, we're taking the limit of this guy as t approaches 20. From the left, well, it's 20 over 20 is 1. So 41 times the square root of 1 is 41, right? So we get the limit from the left is 41. Limit from the right as x approaches 20. That's going to give us just some big numbers. You really don't have to factor anything out of the top. It's probably easier to factor out 100. That probably makes sense. But you could just evaluate this directly also. They're just big numbers, right? You don't need to do that step. Either way, if I plug 20 in and I just crunch the numbers, I'm going to get 41 out of this. Okay? You don't have to do anything fancy there. And then this is important. You have to include this. The value of the function at 20 is 41. So we meet all the criteria for continuity then. Because we have to, that's something I could see students forgetting to put in there, right? But just because the limits exist from the left and the right doesn't mean the function's continuous. You have to show the function also exists and agrees. I would add one more little thing here too that they didn't do. I would take these two pieces right here and say, so therefore, the limit of R of t as t approaches 20 is 41, right? Because the two one-sided limits agreed, okay? Questions? Oh, I guess they said it down here. Never mind. They said it right there. Yes, r is continuous at t equals 20 because the limit of r of t is, as t approaches 20 equals r of 20. Okay? How are we doing? 1-5? Good? I think it's probably last part then. So, okay, so there's the piece from the top again. The company's total accumulated expenses up to time t is modeled by the function e defined by, okay, so here they give us this expense function up here. It's a logarithmic function, base 2 log, where e of t is measured in millions of United States dollars and t is the time in years since 1980. According to these models, is there a time t where t is defined on the closed interval from 0 to 5? T is greater than or equal to 0 and less than or equal to 5, at which the total accumulated profit is equal to 0. Okay, this is a classic intermediate value theorem problem, right? What's the, and we'll review these more and more throughout the year. Before you take the test, I'm going to have you memorize all these theorems, just so you'll know them inside and out. But what is the IVT? What is the intermediate value theorem? This is an existence theorem. All these theorems in calculus, these existence theorems, you just have to provide, you have to meet the criteria, and if you meet the criteria, it guarantees the existence of something, right? So what's the IVT, intermediate value theorem? Want to review that one real quick? Let's do a 30-second review of the intermediate value theorem. So these are all, I call these picture theorems. It's easy just to think about this in terms of a picture. If we've got some value A and some value B, and we've got some function f, this is the one where we say, there's f of A, and there's f of B. If I have some function that's continuous on the, is it open or closed? Say anything here about that? I can't remember, is it open or closed? It'd be open. If the function's continuous on this interval from A to B, and the value of the function at A is, and the value of the function at B are different, and there's some intermediate value, we'll call it K. I think we used K in our textbook. Then if f of A is less than K and f of B is greater than K, and the function's defined in, continuous on this interval, then the function has to pass through that value at least one point. Remember that one? Okay, so you remember going through that. Very simple, used a ton in calculus. So in this case, we've got this function. We just want to show that r of t minus e of t is positive at one endpoint and negative at the other. And as long as the function is continuous on that interval, then it has to have a 0 value somewhere, right? See what we're saying that by the IVT. Okay, so first of all, this function, is it continuous? Well, we already showed that this function is continuous at 20. It's obviously from 0 to 20. That function is continuous. This top piece is where we're looking, right? From 0 to 5, we're looking at this piece, that piece up there, right? That piece is continuous on the interval from 0 to 5. Agreed? Okay. What about this log piece down here? Is this continuous on that same interval? Yeah, it is, right? The only place where log is undefined, you can't take a log of 0, right? But if t runs from 0 to 5, we're plugging positive numbers into the log, so it's also continuous from 0 to 5. So if r is continuous and e is continuous, well, then their difference has to be continuous, right? neither one of those parts blows up, okay? We would then just have to evaluate this difference function, r minus e, at 0 and at 5. So if we evaluate it at 0, r of 0, if we plug 0 in, what's that going to give us? R of 0 is just 41 times the square root of 0. So square root of 0 is 0. So I get 0 as my output of r at 0. What about e? If I plug 0 in for e, I end up getting 3 times the base 2 log of 12 times 0 plus 4. Well, 12 times 0 plus 4 is 4. Let's talk about that log part for a second. So all this part right here is going to become 3 times the base 2 log of 4. Okay, what's the base 2 log of 4? How do you think about that one? Daisy was asking to review logs, and I would probably need to do that. Here's one very short review. We need to take a full day review for sure one of these days. When we start the next unit, that'd be a good time to do it when you guys are working on stuff, working on assignments. Remember the statement, a log is an exponent, right? A good way to do this is to always think about logs in terms of what they would be if I wrote them as an exponent. If I set like something equal to that, like x, the base 2 log of 4, if that's x, how would I write that as an exponential? The base is always the base. The base is going to be the base of the log and the base of the exponent. And a log is an exponent, right? So the log is equal to whatever becomes the exponent. So that's equivalent to saying the base is 2 now for the exponential function. 2 to the x equals 4. Remember that stuff? Hey, Marty. Oh, okay. Julia, got your ASB card. Do you have an ASB card there, President? No? How about that one? You probably want to get one. Yeah. Okay, so does that make sense? Everybody get that? Okay. The other way you could get from here to here, just quick review, would be to do a little, do you see why I put an X there too? Because that's what we're trying to find, right? You guys, you're trying to, the part that you're stumped on, if you're stumped on this, is what is that thing equal to, right? Agreed? So just call it X for a second, right? Because that's the unknown. The other way you could get from there to there would be to do a little bit of math using properties of logs. How would you solve this log equation? How do you undo a log mathematically? Well, you could do, I mean, you could do the base log theorem where you do natural log of 4 over natural log of 2, but you don't know what the natural log of 4 and 2 are. I mean, you could do it that way. There's a ton of ways you could do this. A ton of ways. Well, we really needed, I love teaching this stuff too. This would be a fun one. Let me put a page up here. This is probably a good place to, the base 2 log of 4 equals x. There's a bunch of ways to do this. You could do the equivalent exponential function, because again, the log is equal to the exponent. A log is an exponent. So if you just make that transition where x becomes the exponent, 2 is always the base, then what's left? 4 is on the other side. Okay, you could use the algebra step that if you want to undo a log, you have to exponentiate, right? Exponentials and logs are inverses, so they undo each other. So I could say that now the base is 2. So if I do a base 2 exponential of both sides, so 2 to the base 2 log of 4 is equal to 2 to the x, right? So then that gives us the 2 and the 2 can't, the exponential and the log cancel. So I get 4 equals 2 to the x. Well, we can solve that. 2 to what power is 4? See what I'm saying? Okay. Or I think what Andy was saying was you could write it like this. You could say the natural log of 4, the base 2 log of 4, I could write as the natural log of 4 divided by the natural log of 2. Okay, if I take the quotient of natural log, I could write this, the natural log of 4 is the same thing as the natural log of 2 squared, right? So I could rewrite that as natural log of 2 squared over natural log of 2. I can, by my properties of exponentials, I could pull the x out front, or the 2 out front, sorry, that's a 2, and get 2 log 2 over log 2 equals x. Well, the logs cancel, and now I get x equals 2. There's like a jillion ways to do that one. I would say I would either do it this way or just this way. I mean, to me, that seems like that's the most straightforward and easy way. Okay. Either way, though, what do you get? Well, you get 2, don't you? Oh, and then we get a 3 out front. So this ended up being 2 times 3 is 6. 0 minus 6 is negative 6. Well, that's less than 0, right? So what if we evaluate this difference at 5? R of 5 is 41 times the square root of 5 over 20. Well, square root of 5 over 20 is the same thing as saying 20 I could break down into 2 radical 5, right? So then the square roots of 5 would cancel, and that's just going to give me 1/2, right? So I get 41 halves. Everybody see how we got that? Right? 5 over 20 just reduces to 1/4. That'd be easier. What am I thinking? Square root of 1/4 is 1/2. And then what about over here? I get the base 3 times the base 3 log of 12 times 5 plus 4. So that's 64. Same thing we just did, only with a 64 instead of a 4, right? So we would have just said the base 2 log of 64, if that's equal to x, then what's x? Well, 2 to the x equals 64. 2 to what power is 64? 6. So we get 3 times 6 is 18. So I get 41 halves minus 18. 20.5 minus 18. Well, that's a number bigger than 0. So we get a positive result from our difference at 5. We get a negative result at 0. The function is continuous. And so by IVT, it has to have the intermediate value of 0 at least once on that interval.